Hello, people, and welcome back to the Sleepy Science Lab. Tonight, we're drifting into one of the most daring adventures humanity has ever attempted. The moment a person leaves Earth, everything familiar disappears. There's no air to breathe, no solid ground, no weather patterns, no sound, and no life. Space is a place that doesn't care if we survive, yet we choose to go anyway. We build machines that burn hotter than stars. We train astronauts to push their bodies and minds far beyond normal limits. Against all logic, we keep fragile human life alive in a realm where biology simply isn't designed to function. Space travel isn't safe or natural or comfortable. It's bold, a little terrifying, and absolutely necessary if we want to discover what waits beyond our tiny blue home. If you enjoy these quiet cosmic journeys, feel free to like, subscribe, or share a thought below. It helps more sleepy travelers find their way here. But for now, settle in, let your breath soften, let your thoughts drift, and let your body sink into rest. Let's begin. Spacesuits are essentially personal spacecraft. They may look like clothing, but each suit is a self-contained life support system built to protect a human in an environment where nothing else can. There's no air, no pressure to hold the body together, and temperatures that can swing hundreds of degrees in minutes. Every layer serves a purpose. The inner lining pulls moisture away from the skin. The pressure layer gently compresses the body to prevent bodily fluids from boiling in the vacuum. The outer shell wards off sharp dust, tiny meteoroids, and radiation. The visor is coated with a thin layer of real gold to shield against intense sunlight. And inside the backpack sits a small ecosystem: oxygen tanks, carbon dioxide scrubbers, cooling water tubes, and constantly whirring fans. A single tear could be fatal, which is why every stitch is checked repeatedly. To step outside a spacecraft, an astronaut has to place complete trust in this tiny bubble of Earth they carry into the endless dark. And once they're out there, even their bodies begin to change. Astronauts actually grow taller in space. With gravity no longer pulling the spine downward, the vertebrae slowly separate, adding a few extra centimeters to their height. It feels like a long, luxurious stretch, but it comes with aches and spasms as muscles adjust to their new length. Even basic movements inside a suit or sleeping bag feel slightly different with that extra height. When astronauts return home, gravity compresses the spine back to normal, and that sudden change can be uncomfortable too. Doctors study these shifts closely, because if humans ever build long-term settlements on Mars or giant rotating space habitats, we'll need to understand exactly how gravity shapes the body. Space even has a smell, and astronauts can describe it. No one can breathe in space, of course, but after a spacewalk, a strange scent clings to suits and tools. Some call it hot metal. Others say it smells like burnt steak or welding fumes. The aroma forms when energetic particles from the sun and deep space strike the spacecraft's exterior, creating reactive molecules that mix with oxygen inside the airlock. We never smell space directly, but these chemical traces give us one of the rare sensory bridges between Earth and the void. Meanwhile, the body continues to change. Bones begin weakening almost immediately in microgravity. On Earth, every step you take strengthens your skeleton. In orbit, that pressure is gone. The body stops sending minerals to the bones, causing astronauts to lose up to 1% of bone mass per month. That's faster than even severe osteoporosis on Earth. Weight-bearing bones fade first, like the spine and legs. Excess calcium flows into the bloodstream, straining the kidneys, and eventually leaves the body entirely. To slow this process, astronauts work out for hours every day, using machines designed to mimic resistance in zero gravity. But even then, some loss is unavoidable. Recovery can take years back on Earth, and some astronauts never fully regain their original bone density. If we hope to reach Mars or spend years living away from Earth, solving this problem is one of our biggest challenges. The sun becomes an entirely different thing once you leave Earth behind. Down here, our atmosphere softens its brilliance, scattering harsh light into warm yellows and gentle dawns. But in space, the sun is a blazing white sphere with razor-sharp edges against an endless black backdrop. There's no sky to tame its brightness, no air to tint its glow, and no warning before its heat lands on whatever stands in its path. Without proper shielding, it can scorch metal, fabric, or skin in moments. Shadows are just as intense. They aren't soft or gradual, they're pure darkness with no fading edges. This harsh contrast affects how astronauts judge distance, how solar panels draw power, and even how cameras capture images. Space missions must plan around this unforgiving light, which powers our spacecraft, while threatening electronics and human life at the same time. It's a stark reminder of how gently Earth protects us. Even food in space has to obey the rules of zero gravity. Nothing can crumble, leak, or fall apart, because even a tiny crumb drifting into a vent could cause a mechanical failure. A single drop of soup could float into a control panel. So meals are engineered with precision. Bread is replaced by tortillas because they don't shed flakes. Drinks stay sealed in pouches and are sipped through straws. Fresh produce is irradiated to eliminate bacteria. Even salt and pepper must be mixed into liquids so they don't float away like tiny, spicy asteroids. Taste changes too. Blood shifts toward the head in microgravity, making astronauts feel like they have a permanent stuffy nose, which dulls flavor. To make meals enjoyable, spices are often stronger than they would be on Earth. There are no ovens, no stoves, no refrigerators, just warmers and vacuum-sealed trays. In orbit, cooking isn't art. It's careful, calculated engineering designed to feed without risking anything. Sleeping in space brings its own strange adjustments. There's no bed or mattress, no sense of lying down. Instead, astronauts slip into padded sleeping bags fastened to the wall or ceiling. Without being strapped in, they would drift like balloons, bumping into equipment or even each other. The absence of weight can confuse the brain during dreams, creating sensations of floating, spinning, or falling. Some astronauts find it comforting. Others miss the gentle pressure of gravity. Even when lights are dimmed, the hum of machinery never stops. Fans, pumps, and the occasional creaking of the metal hull reacting to temperature shifts fill the background. The crew keeps a sleep schedule tied to Earth time, even though they may witness a sunrise every 90 minutes outside their window. Rest becomes something learned, not something that comes naturally. Even tears behave differently. Without gravity pulling them downward, they gather into swelling globes that cling stubbornly to the eyes. They blur vision, sting, and are almost impossible to wipe away cleanly. A cloth only spreads the moisture into smaller floating droplets. Tears can drift into the nose or irritate the skin if trapped beneath a contact lens. The only way to clear them is by blinking repeatedly until surface tension breaks and the bubble floats free. In space, even crying reminds you that your body was built for Earth. Of all the challenges astronauts face, spacewalks are among the most dangerous. Stepping out of the airlock into the open void means inviting every threat at once. A tiny puncture in the suit could be fatal. Temperatures can shift from blistering heat to freezing cold in minutes. Even a small accidental push can send a person drifting away from the spacecraft. Everything must be tethered. Breathing must be strictly controlled to keep the suit's atmosphere safe. Every tool is clipped in place. Every movement is rehearsed in giant water tanks on Earth. But even with all that preparation, spacewalks always carry uncertainty. The silence outside isn't peaceful. It's the silence of a place where life does not belong. Inside the spacecraft, another challenge appears: the loss of balance. In microgravity, the inner ear stops sending signals that normally help the brain determine up and down. Suddenly, the body has no natural reference point. Walls, floors, and ceilings all feel the same. Some astronauts adapt quickly, floating effortlessly from place to place. Others experience nausea, dizziness, or disorientation for days as their brain rewires itself to a new kind of motion. Even the simplest actions become puzzles until the brain adjusts to life without gravity. Reaching for a tool, turning a corner, or moving from one module to another can feel strangely unfamiliar. Objects no longer fall when released. Muscles no longer stabilize the body automatically. Every motion must be carefully relearned. This shift in perception is one of the deepest psychological challenges of orbit. Letting go of gravity doesn't only retrain the body, it gently reshapes the mind's sense of home. Beyond these mental adjustments, astronauts face another invisible threat: radiation. Outside the protection of Earth's magnetic field, the body is exposed to a constant storm of cosmic rays, solar particles, and high-speed atoms that slice through everything in their path. These particles can travel straight through metal, skin, and tissue, breaking DNA strands and leaving behind microscopic damage. On Earth, our atmosphere shields us from nearly all of it. In space, astronauts receive doses far beyond safe long-term limits. Over time, this damage can raise cancer risk, weaken the immune system, or cloud the eyes. Engineers are working on better shielding for future spacecraft, but stopping radiation that arrives from every direction remains one of the hardest problems in deep space travel. Every day in orbit reveals something new about a danger that follows astronauts wherever they go. Fire behaves strangely too. On Earth, a flame dances upward as hot air rises and cool air falls. In space, there's no up or down, no rising or sinking. A flame becomes a floating blue sphere, burning slowly and evenly. Smoke doesn't drift upward into the air. It gathers in confused clusters. Fires may be less intense, but also harder to detect. A small flame, hidden in a corner, can fill a room with toxic gases before alarms sound. Because of this, every object on a spacecraft must be tested for how it reacts to fire in zero gravity. Astronauts train for emergencies the same way they trained for spacewalks: sealing hatches, cutting ventilation, finding extinguishers in the dark. Fire on Earth is dangerous. Fire in space is an unpredictable force that can spread in all directions at once. To stay alive, astronauts must exercise every day. On Earth, gravity keeps muscles strong and bones sturdy simply by pulling on them. Without that constant force, the body weakens shockingly fast. Leg muscles shrink, strength fades, and balance becomes compromised. Breathing can even become difficult once astronauts return home. To counter this, astronauts spend hours each day working out using machines that simulate weight. One device uses elastic resistance to mimic lifting. Another recreates running through spinning cycles and tethers. These workouts aren't optional. They're as essential as food and sleep. Scientists are still searching for better ways to protect the body during multi-year missions. Without them, the first humans who reach Mars might be too weak to take their first steps. Even metal behaves differently in space. On Earth, metals usually need heat to fuse together. But in the vacuum of space, exposed metal surfaces can bond instantly through a process called cold welding. With no moisture or oxygen to separate them, atoms from one surface slide into place against another, forming a seamless connection. This can affect tools, robotic arms, satellite panels, or even tiny pieces of debris. To prevent accidental bonding, engineers coat or paint metal surfaces that might touch. It's a small detail with big consequences. A robotic arm could freeze, a panel might fail to unfold, or a hatch could fuse shut. Cold welding reminds us that in space, everyday materials follow different rules. Even taste changes in orbit. Food that feels rich and flavorful on Earth can seem muted in microgravity. Part of the reason is physical. Fluid shifts toward the upper body, causing a constant stuffy nose feeling that dulls smell and taste. The brain also adjusts to the unusual sensation of floating, which influences appetite. To make up for this, astronauts often crave bold, spicy, or tangy foods. Dishes that feel comforting at home might taste bland, while unexpected combinations become favorites. Shrimp cocktail with extra horseradish is known for being one of the top requests. These changes in taste aren't just about enjoyment. They're tied to nutrition, energy, and morale, all of which are crucial for long missions far from home. Long missions demand food that supports both the body and the mind, so every item on the menu is tested to work with altered senses. In orbit, even a single bite becomes part of the science of human adaptation. Another challenge shows up quickly: space sickness. It's similar to seasickness, but hits harder. Our inner balance system evolved to interpret gravity, movement, and body orientation. Remove gravity, and the signals stop matching. The eyes report a still environment, while the inner ear feels a constant freefall. That mismatch can bring on nausea, dizziness, vomiting, and disorientation. Many astronauts face it during their first days in orbit, sometimes so severely that eating, working, or even sitting still becomes difficult. Medical teams prepare for this with medication, gentle routines, and slow exposure to physical tasks. The brain eventually adjusts, but those early days can be overwhelming enough to delay mission plans. And once astronauts return to Earth, the process reverses. Gravity comes back, and so does a second wave of imbalance. Space sickness reminds us that even millions of miles away, our biology is still tied to Earth. Yet space offers moments of unexpected beauty. Inside a spacecraft, astronauts can see shooting stars. When tiny grains of cosmic dust or micrometeorites slam into the hull at incredible speeds, they release bursts of energy that streak like glowing sparks. These flashes appear through darkened windows or sometimes faintly inside dim modules. They're mesmerizing, but not harmless. Each flash marks a high-speed collision that carves microscopic craters into glass and metal. Mission Control tracks clusters of debris and adjusts flight paths to avoid the most dangerous regions. Even so, watching these tiny cosmic sparks reminds astronauts just how thin their metal shelter truly is. Growing plants in space is another challenge that pushes the limits of adaptation. Plants evolved with gravity. Roots reach downward, stems stretch upward, and water settles into soil. In microgravity, none of these rules work. Water forms floating blobs, air pockets don't rise, and seedlings sprout in unpredictable directions. Still, with clever engineering, astronauts have grown lettuce, radishes, and even flowers. Special growth chambers provide light, nutrients delivered through mist or gel, and gentle airflow so leaves don't suffocate. These experiments are more than science. They test the future of life on the Moon, Mars, and beyond. Watching a sprout unfurl among the stars gives astronauts something precious, a reminder of home and a promise that life can travel with us. Inside the human body, changes continue. Blood behaves differently without gravity pulling it toward the legs. Instead, it spreads evenly through the body, gathering in the chest and head. Faces look fuller, legs appear thinner, and blood pressure shifts. The heart no longer works against gravity, so over time it begins to weaken and shrink. Doctors monitor circulation constantly to prevent clots, fainting, or long-term damage after returning to Earth. This change affects vision, temperature control, and even energy levels. It's invisible on the outside, yet every heartbeat in space is another lesson in adaptation. Despite the silence outside, a spacecraft is never quiet. Fans push air through filters, pumps tick, computers hum, valves breathe in steady rhythms. Every sound is part of the machinery that keeps everyone alive. The constant whir becomes a soft background presence, like an artificial heartbeat for the entire station. But the moment an unfamiliar sound appears, the mood shifts instantly. A new vibration or unusual tone could signal a problem somewhere inside the walls. In space, true silence is not peaceful. It's frightening because it might mean a system has failed. Even microscopic life behaves differently in orbit. Some viruses actually become more infectious. Experiments with viruses like herpes and Epstein-Barr showed that in microgravity, under radiation and constant physiological stress, certain viruses can reactivate or replicate faster. Astronauts who showed no symptoms on Earth sometimes displayed signs of viral reactivation in space, even though their immune tests looked normal. Changes in sleep, fluid shifts, and stress all weaken the body's defenses. This discovery adds to the list of challenges for future long-duration missions, where infection control becomes a new frontier in space medicine.
Long space missions demand food that feeds both the body and the mind. That's why every space menu is crafted and tested to work with an astronaut's altered senses. Up there, even a single bite becomes part of the science of human survival. But before astronauts can even enjoy a meal, they face one of space travel's most uncomfortable challenges: space sickness. It's similar to seasickness, only more intense. Our inner ears are designed to understand gravity, motion, and balance. Take gravity away, and the brain gets confused. The eyes report a still environment, while the inner ear reports freefall. That mismatch can trigger nausea, dizziness, vomiting, and disorientation. Many astronauts struggle to eat, work, or even sit still during their first days in orbit. To manage this, medical teams rely on medication, carefully planned meals, and slow physical acclimation. The good news is the body eventually adapts. The bad news is that the discomfort can be intense enough to temporarily interrupt missions. And when astronauts return home, their bodies face a second round of readjustment. Even the spacecraft itself becomes a reminder of how strange the universe can be. Astronauts sometimes see shooting stars from inside the ship. When microscopic dust or micrometeorites strike the exterior at extreme speeds, they release tiny bursts of glowing energy visible through darkened windows. These flashes may look magical, but each one is powerful enough to carve microscopic craters into metal and glass. Mission teams constantly track debris fields, adjusting the spacecraft's path to avoid the worst regions. Yet even these dangerous sparks connect astronauts to the universe, a reminder that ancient dust is still moving across the cosmos. Growing plants in space is another challenge humans are slowly conquering. On Earth, plants know which way to grow thanks to gravity. In microgravity, roots don't know where down is, and stems don't know where up is. Water doesn't sink into soil. Air doesn't rise. Seeds sprout in unpredictable directions. But with clever engineering, astronauts have managed to grow lettuce, radishes, and even flowers in orbit. Special growth chambers use artificial light, nutrient mist, and airflow systems to guide plant development. These experiments are key to future Moon and Mars colonies, where humans will need fresh food and natural oxygen recyclers. Watching a seed sprout among the stars is more than science. It's a reminder that life can travel wherever we dare to go. Inside the human body, space changes everything. Blood flow shifts because gravity no longer pulls it downward. Instead, it spreads evenly through the torso and head. Faces puff up, legs slim down, and the heart suddenly has less work to do. Over time, the heart muscle can weaken. Doctors closely monitor circulation to prevent clots or dangerous drops in blood pressure when astronauts return to Earth. Every heartbeat becomes a small lesson in adaptation. Even the soundscape of a spacecraft takes getting used to. Space outside is silent, but inside the ship, it's never quiet. Fans hum constantly, air moves through filters, and pumps click and whir. These sounds are the heartbeat of the life support system. Astronauts work, sleep, and relax within this mechanical breath. Strangely, the noise becomes comforting.
Silence, however, is terrifying. A quiet spacecraft can mean something has stopped working, and that's the last thing anyone wants to hear. Even microbes behave differently in space. When scientists sent samples of viruses like herpes and Epstein-Barr into orbit, they discovered some became more active under microgravity and radiation. Astronauts who were symptom-free on Earth sometimes showed signs of viral reactivation in space. Stress, disrupted sleep, and shifting body fluids weaken the immune system, making long missions riskier than we once believed. Understanding these microscopic changes is essential for protecting astronauts on journeys that may one day last years. Life aboard a spacecraft also transforms simple routines, like washing. Traditional showers don't work because water doesn't fall. Instead, it forms floating spheres that drift like tiny planets. So astronauts squeeze out small amounts of water or no-rinse soap and wipe down with towels. Even hair washing is done with careful massage and cloth absorption. Every drop counts. Water is too valuable to waste. Lunar explorers face another unexpected danger: moon dust. Moon dust isn't soft like Earth's sand. It's jagged, sharp, and created by billions of years of impact without wind or water to smooth it out. It sticks to spacesuits, scratches visors, clogs joints, and irritates lungs. Apollo astronauts said it smelled like burnt gunpowder. Future missions will require special coatings or electrical systems to repel or shake off dust before astronauts re-enter habitats. Even grooming becomes a carefully controlled operation. In microgravity, cut hair drifts around like tiny meteors. To stop strands from floating into eyes or equipment, astronauts use clippers connected to powerful vacuums. Every tool is tethered. Despite this, stray hairs sometimes escape, drifting silently across the cabin. Grooming might seem simple on Earth, but in space, it helps maintain mental well-being and a sense of normal life. Spacesuits present their own challenges. Spacesuit gloves are built to withstand radiation, extreme temperatures, vacuum, and micrometeorites. But all those layers make fingers stiff and clumsy. Performing delicate tasks during spacewalks feels like trying to thread a needle with thick winter gloves. The pressure inside the gloves pushes back against every move, causing bruises, blisters, and joint pain. Engineers are always working to improve flexibility. But the truth remains, space was never designed for human hands. And sometimes those hands lose things. During spacewalks, tools occasionally float away and become tiny satellites. One astronaut even lost an entire tool bag that orbited Earth for months. Each stray object becomes part of the growing cloud of human-made debris, traveling at dangerous speeds. A single lost screwdriver can puncture a spacecraft. Space is vast, but our orbits are crowded. Finally, when we dream about walking on Mars, there's a reality we can't ignore. Every breath will have to be manufactured. Mars has an atmosphere, but it's almost entirely carbon dioxide. Even a deep inhale would give you virtually no usable oxygen.
Space travel is not safe, natural, or easy. It is bold, it is terrifying, and yet it is the only path forward if we want to see what lies beyond our world. If you enjoy these quiet journeys, consider liking, subscribing, or leaving a thought below. It helps other sleepy souls discover this channel. But for now, all you need to do is relax. Let your mind soften, slow your breathing, and allow yourself to drift gently into rest. Spacesuits are tiny personal spaceships. A spacesuit is far more than clothing. It's a one-person spacecraft designed to keep a fragile human alive in a place with no air, no pressure, and temperatures that can swing hundreds of degrees in minutes. Every layer serves a purpose. The inner lining wicks away sweat, the pressure garment keeps blood from boiling, and the outer shell shields against razor-sharp dust and tiny meteoroids. Even the helmet visor is coated with a thin layer of gold to reflect the sun's harsh rays. Inside the backpack, oxygen tanks, a carbon dioxide removal system, fans, and water circulate through hidden tubes. One tear could be fatal, so every stitch is inspected repeatedly.
Leaving a spacecraft means trusting this tiny, portable world completely. It's a small bubble of Earth carried into the infinite silence. The human body in space. In microgravity, astronauts grow taller as their spines stretch without the constant pull of gravity. This can feel incredible at first, like a slow, satisfying stretch, but it can also cause back pain or muscle spasms. Upon returning to Earth, the spine compresses again, sometimes causing discomfort. Studying these changes helps scientists understand how the body might adapt to life on Mars or in rotating space habitats. Space even has a smell. Astronauts returning from spacewalks describe metallic, burnt steak or welding-like scents clinging to suits and tools. These odors result from high-energy particles interacting with the spacecraft's surfaces, a rare sensory bridge connecting humans to the void. Bones weaken almost immediately in microgravity. Without gravity's constant pull, calcium leaves bones and enters the bloodstream, causing strength loss and strain on the kidneys. Astronauts counter this with hours of daily exercise on specialized machines, but some loss is inevitable, and recovery on Earth can take years. The sun, shadows, and spacelight. Outside Earth's atmosphere, the sun appears as a fierce, blinding white sphere against a pitch-black sky. Shadows are pure darkness, with no gentle gradient to guide perception. This extreme contrast affects how astronauts see depth, operate cameras, and even manage solar panels. The sun reminds us how Earth shields us, softening starlight in ways we rarely notice. Food, sleep, and life's small challenges. Food in space must be safe, stable, and crumb-free. Tortillas replace bread, drinks are stored in sealed pouches, and fruits are irradiated to kill bacteria. Taste changes too. Astronauts often need stronger flavors because fluid shifts and nasal congestion dull the senses. Cooking becomes engineering. Meals must nourish without risking contamination. Sleeping requires being strapped into padded cocoon-like bags to prevent floating into equipment or fellow crew members. Even crying behaves strangely. Tears form floating blobs that cling to the eyes instead of falling. Every small bodily function reminds us how far from home we truly are. Spacewalks are among the most dangerous activities. A tiny tear in a suit could be fatal, and temperatures swing from blistering heat to freezing cold. Astronauts train underwater to prepare, but every excursion into the void carries unknown risks. Adapting to microgravity. In orbit, even simple movements become puzzles. Objects don't fall, muscles don't stabilize automatically, and every motion must be relearned. Microgravity affects not only the body, but also the mind, challenging how astronauts feel at home in their environment. Space radiation presents another invisible danger, damaging DNA and increasing the risk of cancer or weakened immunity. Fires behave unpredictably, forming spheres instead of rising flames, and daily exercise becomes essential to maintain strength. Cold welding, where bare metal surfaces fuse together, is yet another reminder that familiar rules don't apply in space. Even taste shifts dramatically. Food that seems flavorful on Earth can taste bland, prompting cravings for strong, spicy, or tangy dishes. Maintaining nutrition and morale becomes a science in itself. The challenges of long-duration missions. Space sickness strikes many astronauts in the first days of orbit, caused by conflicting signals from the inner ear and eyes. Tiny meteorites create shooting stars visible from within spacecraft, a humbling reminder of the cosmos outside. Growing plants in microgravity requires careful engineering, but it is crucial for long-term missions, offering both nutrition and hope. Blood circulation shifts, faces puff up, legs thin, and hearts can shrink. Spacecraft interiors are never silent. The constant hum of fans, pumps, and electronics forms a rhythmic background that astronauts learn to live with. Viruses may become more active in space, emphasizing the need for vigilance on long missions. Hygiene, tools, and lunar dust. Water behaves like tiny floating planets, requiring careful wiping to stay clean. Lunar dust is jagged and destructive, able to damage suits and equipment. Even haircuts demand vacuum-powered clippers to contain drifting strands. Gloves make simple tasks extraordinarily difficult, and tools lost in space can orbit Earth indefinitely, adding to the growing problem of debris. On Mars, every breath must be manufactured. Oxygen must be generated from carbon dioxide or extracted from frozen water. Habitats require constant maintenance and backups, and the first explorers may stay permanently, building a new home in a harsh, alien world. Rocket burns in space are delicate, precise, and unforgiving. Without atmosphere, flames behave differently, and fuel must carry its own oxygen. Spacecraft face extremes of heat and cold, requiring insulation, radiators, and careful engineering to survive. Martian sunsets are blue, unlike anything on Earth. Iron-rich dust scatters sunlight in ways that transform the sky into a subtle watercolor of blue and warm tones. Future explorers may witness these sights firsthand, seeing sights no human eyes have ever seen. The threat of space junk. Earth's orbit is crowded with debris, abandoned satellites, fragments, and even lost tools. Moving faster than bullets, even tiny pieces can puncture a suit or shatter a spacecraft. Space junk is one of the biggest hazards for exploration, emphasizing the need for careful planning and constant vigilance. Conclusion. Space is a realm of extremes, where survival demands ingenuity, courage, and adaptation. Every breath, every movement, every meal is a triumph over the void. And yet, amid danger and uncertainty, there is wonder. A universe so vast, silent, and beautiful that it continues to call humanity beyond our home. So close your eyes, breathe slowly, and let yourself drift into the gentle embrace of the cosmos.
Zero-gravity toilets and waste management. Without gravity, water doesn't fall and waste doesn't settle. Traditional toilets cannot function in space. Instead, astronauts rely on airflow systems that gently pull waste into sealed containers. Solid waste is compressed and stored for eventual disposal during re-entry, while liquid waste is purified and recycled into drinking water through complex filtration systems. Every step of this process must be reliable and carefully maintained, because a malfunction in the confined space of a spacecraft could be catastrophic. Using the toilet in orbit requires training, patience, and precision. Even the most private moments become exercises in engineering and adaptation. It may not be glamorous, but it is essential for survival. Solar storms, a cosmic threat. The sun, while life-giving, can also be dangerous. Occasionally, it erupts with massive bursts of energetic particles called solar storms. These storms race through space at incredible speeds, striking spacecraft and planets with intense radiation. On Earth, our magnetic field shields us, but astronauts are exposed. During a strong solar storm, radiation inside a spacecraft could reach dangerous levels within hours. Crews must move quickly to shielded areas, often built around water tanks or food supplies. Electronics are also at risk, as high-energy particles can short-circuit systems and damage navigation instruments. Future lunar and Martian missions must include emergency shelters and prediction systems. The sun powers life, yet in space, it also holds the power to endanger life. Running across the moon. The moon's smaller size and weaker gravity make it possible to run around its entire visible horizon in minutes.
Wearing a spacesuit, a trained astronaut could bound in high, slow arcs with each step, while the black sky filled with stars stretches overhead, even at midday. The horizon would curve more dramatically than on Earth, and uneven terrain combined with the suit's bulk makes the run challenging. Yet even this simple act becomes wondrous, a reminder of how every world in space offers unique ways to move, see, and experience reality. Spaceships and their atmospheres. Unlike Earth, a spacecraft cannot rely on natural air. Every breath must be supplied artificially. The cabin atmosphere is carefully engineered with a balanced mix of nitrogen and oxygen, while carbon dioxide scrubbers remove exhaled gas before it reaches toxic levels. Humidity, temperature, and pressure are constantly monitored to prevent condensation or leaks that could endanger life. Backup systems and emergency modes ensure safety, along with oxygen masks and suits in case of sudden depressurization. Future lunar or Martian habitats will expand this artificial atmosphere into entire indoor worlds, complete with controlled airlocks and regulated environments. Air in space is never a given. It is a fragile gift, carefully built, protected, and renewed every moment. Orbit, falling forever. The International Space Station may appear to float, but it is in constant free fall toward Earth. Its forward speed ensures that as it falls, the planet curves away beneath it, creating continuous orbit. Inside, astronauts feel weightless because they are falling along with the station, experiencing no acceleration, just a gentle drift that makes everything float. To maintain orbit, boosters or visiting spacecraft periodically adjust its trajectory. Orbit is not the absence of gravity, it is the art of falling forever while racing around the Earth at incredible speed. Scent of the stars. Some telescopes detect more than light. They capture radio waves and chemical signals from clouds of gas and dust between stars. Among these are molecules like ethyl formate, the compound that gives raspberries their distinctive scent. Other clouds reveal alcohols, carbon rings, and organic molecules that could form the building blocks of life. Through these signals, the cosmos leaves a trace of its invisible chemistry, a reminder that even the vast emptiness between stars can carry the subtle essence of life.
Smelling the galaxy. By translating cosmic signals into sensory forms, such as smell, scientists can imagine what it might be like to walk among the clouds of our galaxy. The Milky Way contains everything from bitter molecules forged in dying stars to sweet compounds drifting near newborn suns. These scents are never directly inhaled, yet they hint at the strange chemistry of the universe and the shared building blocks between distant nebulae and life on Earth. Astronomy, in this sense, becomes a multi-sensory science, not just observation, but an invitation to taste, touch, and smell the cosmos through the tools we create. Time dilation and deep space travel. Time is not uniform for everyone. According to Einstein, movement and gravity affect its passage. Astronauts aboard the International Space Station experience slightly less gravity and move at high speeds, causing them to age just fractions of a second less than people on Earth over months. Though tiny, this effect is measurable. Imagine future explorers traveling near light speed toward distant stars. Time for them could pass much slower than on Earth, with decades or centuries slipping by for those left behind. They might return to find entire generations gone. This is not science fiction. It is written into the laws of physics. Deep space travel may one day make time itself a landscape humans must navigate. Relearning to walk on return.
After months in microgravity, astronauts' bodies forget how to balance, carry weight, or coordinate steps. Bones lighten, muscles shrink, and nerve endings practice sending correct signals. Returning to Earth, even standing can feel challenging. Blood rushes downward differently, causing dizziness. Doctors and trainers work closely with each astronaut, using harnesses, treadmills, and targeted exercises to rebuild strength and coordination. The process can take weeks or months, offering a preview of the challenges humans might face on Mars or other worlds with different gravity. Relearning to walk is not just a physical struggle, it is a deeply emotional reminder of how our bodies are shaped by the worlds we inhabit. Mars's long-lasting storms. Mars may seem calm from a distance, but its winds can create storms lasting months. Powerful gusts lift fine dust into massive storms that can spread across the entire planet, dimming sunlight even at midday. The dust, sharp and chemically reactive, can clog equipment, reduce solar power, and coat every surface. Global dust storms create fluctuating temperatures and pressures that challenge landers, habitats, and future human explorers. Living on Mars will require shelters that can withstand these conditions and systems that can operate with minimal sunlight for extended periods. On a planet of red dust, weather becomes a force capable of reshaping every mission plan. Medical mysteries of space. Every mission into deep space reveals new biological challenges. Microgravity affects bones, muscles, circulation, and vision, but the long-term effects on the heart, nervous system, immune response, and mental health are still being studied. Fluid shifts can increase eye pressure. Dormant viruses may reactivate. Balance circuits in the brain reorganize, and even wound healing can behave differently. Each mission becomes a living experiment, showing how deeply life on Earth is optimized for Earth itself. To thrive far from home, humans may need to rethink every aspect of biology. Micrometeorites, the invisible threat. Space is filled with tiny fragments of rock and metal, micrometeorites, left from planetary formation or collisions. Many are smaller than a grain of sand, but travel tens of thousands of kilometers per hour. Even such small particles can pierce metal, glass, or a spacesuit at those speeds. Spacecraft use layered armor to absorb impacts, and suits have reinforced plating. Tanks or modules sometimes double as protective shields. While large debris can be tracked, micrometeorites are too small to detect, making every mission a risk-filled journey through a cosmic shooting gallery. Even the International Space Station bears small craters and scratches from past impacts. Protection in space is a delicate balance of weight, material, and engineering. Earth's weather from space. From orbit, Earth appears as a living, swirling painting. Storms spin across oceans like miniature galaxies, offering a breathtaking perspective of our planet's dynamic systems. Observing Earth from space reveals not only beauty, but the intricate forces that govern climate, weather, and life itself.
Watching Earth's weather from orbit. From space, clouds stretch across continents in delicate threads, and lightning arcs silently through storms. Astronauts can observe entire hurricanes forming and moving below, watch rain shadows creep across deserts, and glimpse the soft glow of city lights beneath layers of cloud.
From this vantage point, weather becomes a global ballet shaped by sunlight, air, and rotation. Observing Earth this way helps scientists understand storm formation, climate shifts, and the exchange of heat between oceans and the atmosphere. It also offers a humbling reminder of the planet's fragility. Every storm, shadow, and river of cloud is part of a single interconnected system that sustains life. From above, Earth is not just a planet, it is a living home, wrapped in air and water, vibrant with motion and color. Radiation, the invisible hazard. Every spacecraft has a strict limit on safe radiation exposure. Space is filled with invisible rays from stars, galaxies, and high-energy particles. On Earth, our atmosphere and magnetic field shield us, but in orbit, astronauts and electronics are constantly exposed. Each mission calculates the total radiation dose the crew can safely tolerate, taking into account age, gender, and mission length. In traffics DNA, weakening the immune system, or increasing cancer risk. For electronics, radiation can corrupt memory, destroy circuits, or permanently disable systems. Engineers design protective shielding, but added protection increases spacecraft weight, forcing a delicate balance between safety, efficiency, and mission goals. In space, the invisible can be deadly, and every journey is measured not just in distance, but in dosage. Sound and silence in space. Sound cannot travel through the vacuum of space, but vibrations can. Without air, a scream, explosion, or roar is silent to human ears. Yet vibrations pass through solid objects, letting astronauts hear the hum of machinery, the creak of metal expanding in sunlight, or a gentle knock on a wall. In space, sound exists as a vibration in shared surfaces rather than a wave in the air. Instruments that detect gravitational waves can even translate distant cosmic events into low, eerie tones perceptible through speakers. Outside a spacecraft, spoken words only travel through electrical communication, not air. The silence of space is profound, broken only by the steady hum of life support, the buzz of your suit, and the rhythm of your own breathing within the helmet. Footprints on the Moon. The first footprints on the Moon remain untouched. When Apollo astronauts stepped onto its surface in 1969, they left behind boot prints, tool marks, and lunar rover tracks. With no wind, rain, or significant geological activity, these impressions may persist for millions of years. Even meteoroid impacts are rare enough that many remain undisturbed. These marks act like frozen fossils of human exploration, capturing a brief moment when humans walked on another world. Future explorers may stand beside footprints made decades earlier, seeing the surface exactly as it was. It is a haunting, beautiful reminder that in places without weather, every human touch becomes permanent. The fragility of spacecraft. A tiny hole in a spacecraft can be catastrophic. Spacecraft are sealed containers, holding back the vacuum with layers of metal, insulation, pipes, and wiring. Even a hole the size of a grain of sand can trigger a slow, dangerous air leak. This may happen from micrometeorites, space debris, or even construction errors. Astronauts are trained to locate and patch leaks quickly using sealants and emergency covers. The inside of a spacecraft is a fragile bubble of Earth suspended in nothingness. Any failure can turn familiar air into a dwindling resource. Engineers counter these risks with layered walls, alarms, and redundant systems, but the threat is ever present. In space, the line between life and vacuum can be thinner than a sheet of paper. Golden helmet visors. Astronaut helmet visors contain real gold. The thin coating, almost invisible to the eye, protects against the sun's intense radiation during spacewalks, reflecting harmful rays while allowing clear vision. It is a subtle, elegant solution to one of space's many invisible dangers.
Gold visors, ancient material, modern shield. Gold is a remarkable protector in space. Its reflective properties block dangerous infrared radiation, shielding astronauts' skin and eyes from scorching sunlight. Unlike many metals, gold does not tarnish or react with oxygen, making it durable even under extreme conditions. On a sunlit spacecraft, the thin gold layer keeps astronauts cool while guarding against ultraviolet rays that Earth's atmosphere would normally filter. Helmet visors are layered with multiple materials, but gold acts as the frontline shield, standing between the astronaut and the raw glare of the sun. In the emptiness of space, something as simple as gold becomes a vital tool for survival, a symbol that ancient materials can still serve cutting-edge technology. Bacteria in space. Life finds a way. Scientists have sent bacterial samples into orbit and even beyond to see how life survives the harsh conditions of space. Some microbes endure vacuum, radiation, and temperature extremes for years by entering dormancy, while others thrive, multiplying faster or developing stronger antibiotic resistance. Experiments placing bacteria on the exterior of the International Space Station have returned them to Earth still alive. These discoveries raise profound questions about the origins of life. Could primitive organisms have traveled between planets on meteorites, seeding worlds with biology? Studying microbes in space also informs human health for long-duration missions. Microbes evolve quickly, adapting to space far faster than human cells. These findings highlight the resilience of life and suggest that space may not be as biologically empty as it appears. Materials in microgravity, stronger and flawless. Some materials grow stronger in zero gravity. On Earth, gravity can pull on atoms during solidification, creating imperfections or uneven density. In microgravity, metals and crystals can form more uniformly, producing flawless structures. Ultra-pure crystals grown in orbit are being tested for medical devices, electronics, and spacecraft components. Some alloys even gain new properties when solidified in space, free from sedimentation or convection. Microgravity offers a near-perfect laboratory for studying matter. One day, engines, electronics, or even spacecraft parts may be built with materials impossible to make under Earth's gravity. Even a simple metal bar forged in space could hold secrets unattainable on the ground. Psychological preparation. The mind before launch. Spaceflight is as much a mental challenge as a physical one. Astronauts spend years learning technical skills and emergency procedures. But emotional readiness is equally critical. Living in confined quarters, far from home, without sunlight or fresh air, creates stress unlike anything on Earth. To prepare, astronauts train in isolation chambers, underwater habitats, and remote locations, rehearsing calmness and emotional resilience. Psychologists guide mindfulness practices and coping strategies for fear, boredom, and uncertainty. Even seeing Earth from orbit can trigger awe, loneliness, or profound responsibility. Preparing the mind for space begins long before liftoff. It requires shaping the spirit to embrace silence, danger, and wonder without losing focus. Crying in microgravity. Even tears behave differently in orbit. Without gravity, they do not roll down the cheeks, but gather into shimmering spheres, clinging to eyelids until they overflow or float away. Stress and isolation intensify emotions, making crying more noticeable and challenging. Astronauts learn to gently wipe tears using cloths or tools to prevent them from drifting into equipment. Crying in space becomes a reminder of human vulnerability. Even weightless, emotions remain real,
and the body behaves in ways that defy earthbound instincts. The vacuum of space. Deadly yet subtle. Exposure to the vacuum of space is lethal. Without pressure, bodily fluids, including blood, begin to boil, even at normal temperature. Oxygen escapes from the lungs, gases expand in the bloodstream, and consciousness is lost within seconds. Contrary to dramatic movie portrayals, the body does not explode, but it sustains rapid, irreversible damage. The vacuum of space is unforgiving, reminding us that life survives here only with careful protection.
Spacesuits are more than clothing. They are pressurized mini spacecraft, creating an environment that mimics Earth inside layers of protection. Every layer shields astronauts from radiation, extreme heat and cold, and the deadly vacuum of space. In this void, the absence of anything, air, pressure, resistance, poses the ultimate threat. Life can unravel in an instant if the suit fails. Landing on Mars, a high-stakes challenge. Touching down on Mars is like trying to stop a speeding car on ice. The thin atmosphere provides barely any resistance, making parachutes less effective and rockets essential but fuel-intensive. Dust storms can obscure sensors, and the surface offers no dense air to slow a descent. Spacecraft arrive at tremendous speeds and have only minutes to slow down, navigate obstacles, and land safely. Engineers rely on airbags, retro-rockets, sky cranes, and heat shields, testing each system repeatedly, but failures still happen. Landing on Mars is one of the greatest obstacles to human exploration, a delicate balance between risk and reward written in fire and dust. Privacy in orbit, a shared life. Life in space is lived in extremely tight quarters. The International Space Station offers tiny sleeping pods, roughly the size of a closet, but astronauts hear machinery hum and the muffled movements of crewmates. Conversations are often overheard, cameras and sensors run constantly, and bathrooms are shared. Even communications with Earth are monitored and sometimes delayed. Privacy becomes less about being alone and more about managing thoughts and emotions amid constant proximity. In space, moments of quiet reflection are hard-earned victories. Hygiene in microgravity. Damp towels and ingenuity. Showers as we know them don't exist in orbit. Astronauts clean themselves with rinseless soap, water pouches, and absorbent towels. Small droplets of water are carefully massaged onto the skin and wiped away. Hair is washed with minimal water, combed, and dried with suction fans. Microgravity makes water behave unpredictably, forming drifting spheres that cling to surfaces or float into equipment. Personal hygiene is more than comfort. It's a small reclamation of normalcy in an environment designed for machines, reminding astronauts of the everyday luxuries we take for granted on Earth. Floating experiments, science without gravity. Every astronaut doubles as a scientist, conducting experiments on cells, fluids, combustion, and materials that behave differently in microgravity. Equipment must be secured, liquids stick, pool, or float unpredictably. Microgravity allows unique studies impossible on Earth, from protein crystal growth to observing how fluids mix when weightless. Astronauts develop incredible dexterity, learning to assemble labs mid-air and capture free-floating samples. Even stirring a solution becomes a scientific challenge. Each experiment expands our understanding of biology, chemistry, physics, and engineering, knowledge critical to safer spacecraft, more effective medicine, and living beyond Earth. Windows in space. Constant vigilance. Spacecraft windows are layered polycarbonate and fused silica, built to withstand micrometeoroid impacts. Tiny particles traveling faster than bullets leave pits and scratches, distorting vision and weakening the material. Stations track debris and orient windows away from danger when possible. Some windows feature removable panels or protective shutters, while others are replaced once damage reaches a critical level.
every glance at Earth or the stars is both a privilege and a reminder of the hazards outside, a view earned through constant vigilance.
Marks of collision. Windows of the universe. Every scratch or pit on a spacecraft window is a tiny signature from the cosmos, a mark left by particles traveling at incredible speeds. These imperfections are reminders that even in the emptiness of space, the universe leaves its trace. Mars. Seasons twice as long. Mars has seasons, but each one lasts nearly twice as long as on Earth because the planet takes almost 2 Earth years to orbit the Sun. Winters are bitterly cold, while summers are milder but dusty, often accompanied by planet-wide storms. Mars's tilted axis creates shifting sunlight patterns that sculpt weather throughout the year. Ice caps grow and retreat, carbon dioxide freezes and thaws, and winds carve sand dunes into ever-changing shapes. For future settlers, adapting to Mars will mean adjusting to stretched seasons, thinner air, and freezing nights. Living in a calendar where time itself feels slowed by the rhythms of a distant world. The view from low Earth orbit. From the International Space Station, astronauts circle the globe in about 90 minutes. Entire continents pass beneath them. Oceans glimmer like silver threads. Mountains and cities sweep by, and cloud systems drift across landscapes. Sunrises and sunsets arrive every 45 minutes, painting skies in gold and indigo. Lightning flashes illuminate storms like glowing veins. National borders fade from view, replaced by the sense of a single, fragile planet. Many astronauts experience the overview effect, a profound shift in consciousness that comes from seeing Earth as one interconnected home, floating silently through space. Electrostatic charging, energy and risk. As spacecraft move through charged particles in Earth's magnetic field, static electricity can build, creating sparks or shocks that may damage electronics or ignite fires. Engineers design systems to safely bleed off excess charge or redistribute it across surfaces. In some cases, spacecraft can even harness this effect to generate power, but it must be carefully controlled. In space, silence and emptiness themselves become sources of energy and risk. The weight of spacesuits. A fully equipped spacesuit, including reinforced layers, pressure systems, communication devices, oxygen tanks, and cooling tubes, can weigh over 100 kilograms on Earth, often more than the astronaut inside it. In microgravity, the suit floats effortlessly, but on Earth, training in it can be exhausting. Each suit is custom-made, tailored to the wearer, and designed for the mission ahead. Gloves alone are marvels of engineering, providing both protection and precision. Essentially, a spacesuit is a spacecraft in clothing form, carrying life support, shielding, mobility, and communication. Heavy on Earth, invaluable in space. Who owns space? Space was once a borderless frontier, governed by treaties forbidding any single nation from claiming celestial territories. Today, private companies aim to mine asteroids, nations plan permanent lunar bases, and satellite orbits fill at unprecedented rates. Questions about ownership, rights, and access are multiplying faster than laws can keep pace. Human ambition is reaching every corner of the cosmos, sometimes faster than our rules can follow. Breathing in space, a manufactured necessity. Unlike Earth, where air is effortless,
Every breath in space is carefully engineered. Oxygen must be stored in tanks or produced from water through electrolysis. Carbon dioxide is scrubbed from the air using chemical filters to prevent toxic buildup. Even breathing, one of the simplest acts on Earth, becomes a technological challenge when far from home.
Where you can direct a voice, create realistic dialogue, and so much more. Edit these placeholders to get started.
Atmosphere, a fragile machine. In space, humidity must be carefully controlled to prevent mold, rust, or equipment failure. Every system, from air circulation to filtration, relies on electricity, material science, and redundant engineering. If a single component fails, a clogged filter or broken pump could make the atmosphere hazardous within minutes. Breathing becomes a deliberate process, not an automatic reflex. Every inhale reminds astronauts how alien life is outside Earth's cradle, where air is no longer a gift, but a machine we must maintain. Robotic pioneers on Mars. Before humans foot set on Mars, robots may arrive years in advance to build the first habitats. Using the planet's soil, known as regolith, mixed with special binders, robotic constructors could 3D print walls and shelters. They might also dig trenches for wiring, assemble solar arrays, and install life support systems for incoming crews. These automated builders would transform the barren surface into a quiet worksite, readying a safe foothold long before the first human steps on Martian soil. By the time astronauts arrive, homes, power, and pressurization could already be waiting, reducing risk and effort on arrival. For now, these technologies are tested in deserts, Antarctica, and other isolated environments on Earth. The first structures on Mars may very well be created by machines long before humans inhabit the red planet. Water, floating wonders. In microgravity, water behaves like living jelly. It forms spheres that drift, wobble, and stretch like tiny planets of shimmering glass. A gentle touch breaks one into smaller droplets, each quivering with surface tension. Water clings to fingers, cheeks, and equipment, and astronauts cannot drink from open containers. They sip from sealed pouches to prevent droplets from floating into machinery. Even washing becomes a careful exercise in control. Without gravity, surface tension dominates, turning water into a playful, almost sentient force that reminds astronauts how the familiar becomes the extraordinary in space. Personal keepsakes, a touch of home. Even in the highly scheduled, efficient life of a space mission, astronauts are allowed a single personal item, a small memento from home. It might be a childhood toy, a family photo, a national flag, or a wedding ring. Packed carefully among tools and equipment, it becomes a grounding object in a world dominated by machines and silence. Many choose items that represent people or memories they cannot leave behind. Once in orbit, the keepsake is a comfort. Upon return, it becomes a relic of space travel, forever changed by its journey beyond Earth. Sunrise every 90 minutes. Orbiting Earth, the International Space Station completes a circuit every 90 minutes, allowing astronauts to watch the sun rise and set about 16 times per day. As the station approaches the edge of light, a thin arc of color appears along the horizon, shifting from deep indigo to orange and bright white. The blue glow of Earth's atmosphere seems almost unreal from above. In just 45 minutes, the sun dips again behind the planet, casting the surface into shadow, where city lights sparkle like constellations of their own. In this rapid cycle, day and night are measured not by clocks, but by the turning of Earth beneath a silent spacecraft. Sunlight never fully settles, and night never lingers. The trail of human exploration. Human missions leave behind a scattered legacy across the Moon, Mars, and beyond. Footprints, tools, rover tracks, flags, and even a family portrait mark the Moon. Mars hosts landers, heat shields, parachutes, and rover trails across ancient soil. In orbit, old satellites drift alongside screws, paint flakes, and lost tool bags. Some items are deliberate, others are remnants left because they were too risky or unnecessary to bring home. These artifacts form a silent archaeology of exploration, reminding us that every journey changes both the traveler and the place they visit. Future explorers may one day study them as the first relics of humanity venturing beyond Earth. A spaceship is a self-contained world. A spacecraft carries everything needed to survive: fire, air, food, water, and even simulated gravity. It is a self-contained ecosystem designed to sustain life in a place with no air, no soil, no weather, and no external help. In space, humans do not just travel, they live within a machine engineered to replicate the essentials of home.
Where you can direct a voice, create realistic dialogue, and so much more. Edit these placeholders to get started.
Life support, machines that breathe. A spaceship must create breathable oxygen, filter harmful carbon dioxide, and regulate temperature and humidity. Food is stored in sealed packages for months or even years, remaining safe to eat when opened. Water must be endlessly recycled, as every drop is precious. Fire exists only in controlled systems, and any stray spark must be prevented from spreading. Since gravity is absent, the vessel must simulate it or counter its effects, often through exercise machines or rotating sections, to keep muscles and bones from deteriorating. The ship becomes a miniature Earth held together by technology rather than nature, where every breath and bite depends on flawless machinery amidst silence and vacuum. The sounds of a living station. The International Space Station is never truly quiet. Fans hum, motors adjust position or pressure, and air circulates constantly. As the station moves from sunlight into shadow, its metal walls expand and contract, producing soft pops, groans, and clicks, like an old sailing ship shifting on invisible waves. Vibrations from nearby modules travel through the structure, reminding astronauts that they are never alone. Earplugs or white noise machines help sleep, but these subtle sounds also signal that life and systems are functioning correctly, a comfort in the vastness of space. Spacesuits, pressurized balloons of life. A spacesuit is more than protective clothing. It is a pressurized life support system. The internal pressure keeps the astronaut's body safe from the vacuum outside. Inflated to a safe level, the suit pushes against the skin, making movement stiff and laborious. Every bend of the arm or turn of the head feels like flexing inside a resistant balloon. Engineers solve this with rotating joints, layered materials, and temperature regulation systems. The suit also provides oxygen, scrubs carbon dioxide, shields from radiation, and protects against extreme temperatures and high-speed particles. Without it, even breathable air would not save the astronaut. The suit itself is life zipped and sealed around a single human floating in emptiness. Venus, the fiery furnace. Compared to Venus, Mars almost feels welcoming. Venus reaches temperatures of nearly 500 degrees Celsius, hot enough to melt metal, and has a crushing atmosphere rich in carbon dioxide and sulfuric acid, 90 times denser than Earth's.
Landing is like plunging into a boiling, toxic ocean. Robotic landers survive only a few hours before succumbing to heat and pressure. Yet Venus was once more Earth-like, with oceans and possibly a mild climate. Studying it reveals how planets evolve and why Earth remains habitable. For now, Venus remains a world to observe from afar, its dangers too extreme for human exploration. Space farming, growing life beyond Earth. To become a multi-planet species, humans will need to grow food independent of Earth. Plants can flourish in hydroponic systems under artificial light, as demonstrated aboard the International Space Station, where astronauts have grown lettuce, radishes, and flowers. These crops provide fresh nutrients and recycle air by absorbing carbon dioxide and releasing oxygen. Future farms on Mars or lunar bases might use water from ice, composted waste, and nutrient gels instead of soil. Plants may adapt to low gravity with unique shapes or structures. Space farming not only sustains life, but brings a touch of Earth to sterile, remote environments. Artificial gravity, spinning homes in space. Lack of gravity is one of the greatest challenges for long-term space living. Without it, bones weaken, muscles shrink, and even the heart reshapes. Rather than relying solely on exercise, future habitats could generate artificial gravity through rotation. Giant rings or spinning sections of space stations would push everything outward via centrifugal force, mimicking Earth-like gravity. Floors would feel flat, allowing inhabitants to walk, sleep, work, grow food, and raise children naturally in an environment far from any planet. Spinning habitats could transform life in space, making distant worlds feel like home.
Spinning habitats, homes among the stars. If successful, these rotating habitats could become humanity's first permanent homes in space, not just a place to visit, but a world where entire generations grow up inside slowly turning rings, creating their own sense of down, sky, and ground. Life in such homes would feel natural, yet entirely alien, a new way of experiencing the cosmos. Living with constant danger. Life in space means accepting that almost everything around you can be deadly in an instant. Outside the window, there are no oceans or forests, only a vacuum so cold and empty it would instantly boil the moisture in human lungs and eyes. A single broken seal, fire spark, or burst pipe could fill a spacecraft with smoke or poison. Solar storms, cosmic debris, and extreme environmental hazards move silently through the void. Even sleep requires careful strapping to walls so astronauts do not drift into equipment. Astronauts train not just for science, but for survival, repairing systems, providing emergency medical care, and mastering mechanical skills. Over time, danger becomes part of the background, like the wind or rain on Earth. Trust in their ship, training, and crewmates is what keeps them alive hour after hour in a world where forces do not care whether humans survive. Human evolution beyond Earth. If humans raise children on Mars or other worlds, evolution may follow new paths. Lower gravity could affect height, posture, and the strength needed to move. Bones might grow longer or lighter. Muscles in legs and back might weaken, and hearts could adapt to pumping in a different gravitational field. Children raised on Mars could feel heavy and sluggish if brought to Earth. Skin color may change under new levels of ultraviolet light, and balance and vision may adjust to unfamiliar gravity. Over centuries, these differences could become pronounced, potentially creating humans suited for other planets in ways that diverge from Earth-born physiology. Space won't just change our technology, it could change us. The moon's dust, sharp and dangerous. Apollo
astronauts noticed lunar dust smelled like gunpowder after returning inside their module. Space itself has no air, so the scent appeared only when oxygen met the fine gray dust coating suits. Lunar dust is razor sharp, formed by billions of years of meteoroid impacts, and it clings stubbornly to skin, equipment, and lungs. Chemical reactions between oxygen and elements like iron and silicon produce the distinctive gunpowder smell. In future lunar settlements, this dust will be a major hazard, capable of damaging machinery, harming lungs, or blocking air filters. Even seemingly benign ground can be deadly on another world. Dead satellites, ghosts of the sky. Non-functional satellites do not fall to Earth. They drift silently for decades or centuries, posing collision risks. Thousands of inactive machines, from weather monitors to early communication satellites, circulate in orbit. Some are moved to graveyard orbits, but many remain adrift, threatening active spacecraft. Even tiny fragments moving faster than bullets can rip holes in solar panels or destroy sensitive instruments. A collision between two dead satellites can trigger a chain reaction called the Kessler effect, creating clouds of debris that endanger space travel for years. These silent, drifting satellites are reminders that our actions in space have long-term consequences. Space mining, resources beyond Earth. Asteroids hold immense wealth: platinum, nickel, gold, and other rare metals far surpassing the reserves of Earth's mines. Some are rich in frozen water that could be converted into rocket fuel, breathable air, or drinking water. Mining these celestial bodies could power civilizations, providing the raw materials and resources for humanity to expand into the solar system. Where you can direct a voice, create realistic dialogue, and so much more. Edit these placeholders to get started.
Space mining, fueling the future. If humans master asteroid mining, we could sustain entire space stations or planetary outposts without relying on constant shipments from Earth. A single asteroid just a few hundred meters wide could provide enough metal to build thousands of spacecraft. Water in deep space could be harvested to refill tanks between planets. Scientists are already mapping which asteroids contain valuable resources and designing autonomous robots capable of landing, drilling, and extracting materials without humans on site. Companies are preparing to claim mining rights once international laws allow it. One day, space industry may operate entirely independent of Earth. Factories in orbit could construct ships, solar arrays, habitats, and satellites using metals harvested directly in vacuum. Space mining could power an interplanetary civilization, much as coal once powered industry and oceans fueled trade. Magnetic shields, protecting life in deep space. Spacecraft must carry their own protective magnetic fields. Earth's magnetic field shields us from deadly solar radiation by diverting high-speed particles. Once a spacecraft ventures far from Earth, that protection fades, exposing the crew and electronics to intense radiation capable of damaging DNA, triggering hallucinations, or destroying equipment. One proposed solution is to give spacecraft artificial magnetic fields using coils of electricity or plasma, creating a protective bubble around the ship that deflects harmful particles, like wind shielding a flame from sparks. The challenge is generating a strong enough field without consuming too much energy. If perfected, this technology could allow safe human travel to Mars, Jupiter's moons, or even the outer planets, turning radiation from a deadly hazard into a manageable obstacle. The first Martian child. The first human born on Mars will never be entirely Earthling. In 1/3 gravity, a newborn's heart, spine, and bones will develop differently, shaped by a sky, pressure, and light unlike anything on Earth. Their first words might describe objects or concepts that do not exist on our planet. Their immune system will adapt to a colony-specific environment, not forests, oceans, or farms. If they grow up never setting foot on Earth, returning may feel strange and heavy. This child represents the beginning of a new branch of human experience, shaped not by Earth, but by the raw red horizon of another world. Seeing the invisible. Astronauts observe light beyond what human eyes can detect. Sunlight contains ultraviolet, infrared, and other radiation blocked by Earth's atmosphere. Special cameras reveal warm objects glowing in total darkness, stars burning in ultraviolet energy, and heat leaking from spacecraft. Electrical storms at sea can be seen as ultraviolet fire, hidden from natural vision. These tools transform the astronaut's perception, unveiling a universe of colors, forces, and phenomena humans never evolved to see. Space does not just extend our reach, it expands our senses. Time in space. Time in space is relative to Earth. On Earth, time is measured by sunrises, sunsets, and seasons. In orbit, the International Space Station circles Earth every 90 minutes, producing 16 sunrises and sunsets each day. Astronauts maintain Earth-based clocks to schedule sleep, exercise, and experiments. Mars has slightly longer days, the Moon nearly a month-long day, and deep space has no natural time at all. Calendars and birthdays become abstract in the vacuum, existing only because humans carry them, a memory of where we came from and the rhythms of our home planet. Running on an asteroid. Many asteroids are tiny compared to planets. On one, an astronaut could run around the entire surface in minutes. Gravity is minimal. A human might weigh just a few grams. Every movement changes. Jumps send you soaring, and each step floats you gently back down. Asteroids transform basic physics into a new dance of motion, reminding humans that even gravity itself is negotiable among the stars.
Moving on asteroids, flying in slow motion. On small asteroids, a fast run becomes a series of gentle, controlled hops, almost like flying in slow motion. Astronauts would need magnetic boots, tethers, or handholds to stay attached while exploring. Momentum must be carefully managed, or a misstep could send someone floating off into space. Every movement becomes a reminder that in the universe, the rules of motion are dictated by the size and gravity of the world beneath your feet. Mars time, a new calendar. Future settlers on Mars will need entirely new calendars. A Martian day is roughly 40 minutes longer than an Earth day, and a year lasts nearly twice as long. Seasons are stretched, sunlight changes differently, and even the length of a shadow at noon follows new rules. Colonists will rely on Martian-based clocks and calendars to schedule work, school, planting cycles, and celebrations. Months might be tied to the motions of Mars's tiny moons, Phobos and Deimos, and year numbers could begin with the first human landing. Birthdays, too, will shift, as one Martian year nearly equals 2 Earth years. Time itself will become a part of identity, shaped by the rhythms of another world. Solar shields, defending against the sun. Every space mission must carry protection against the sun. Beyond Earth's magnetic field, high-energy particles and radiation can be deadly. Spacecraft use shields to block, reflect, or absorb solar energy. Some look like shiny panels. Others are thick layers of water, metal, or specialized plastics. On Mars missions, astronauts may use storm shelters inside their ships, protected by extra radiation shielding, while spacesuits themselves contain layers to block ultraviolet light and charged particles. Without this protection, computers fail, equipment breaks, and humans could suffer radiation sickness within hours. The sun is life-giving, but in space, it is also a force that demands respect and preparation. Simulating Mars on Earth. To prepare for life on Mars, scientists have built Earth-based simulations in deserts, ice fields, and volcanic craters. Volunteers live inside these mock habitats for weeks or months, cut off from normal contact. They wear bulky suits, eat shelf-stable food, and communicate via delayed messages to mimic the time lag between Earth and Mars. They grow plants under artificial lights, test water recycling, and study the effects of isolation on mental and emotional health. These experiments answer critical questions: how to solve conflicts in small groups, maintain air quality without trees, and repair equipment when stepping outside requires a suit. Every hour spent in these environments brings humanity closer to sustainable life on another planet. Space debris, a threat to humanity. Earth's orbit is increasingly crowded with abandoned satellites, fragments, and rocket pieces. Even tiny debris can be deadly, moving faster than bullets. Collisions can trigger a cascade of fragments, known as the Kessler effect, potentially making space travel impossible. Satellites that support navigation, communication, and weather could be lost, and human missions could be trapped on Earth. Cleaning up this debris is difficult, but solutions are being developed. Nets, magnets, giant brooms, or small spacecraft that push debris into the atmosphere to burn up. The future of space travel depends not just on exploration, but on cleaning up the mess humanity has left behind. Lunar underground settlements. Living on the Moon will likely require underground settlements. Its surface is beautiful yet hostile. No air, extreme temperature swings, and exposure to radiation and micrometeoroids. Underground tunnels or caves can provide shelter from these hazards. Lava tubes, ancient tunnels formed by flowing molten rock, may be large enough to house entire neighborhoods, farms, laboratories, and factories. Sealed and filled with breathable air, these subterranean habitats could make the Moon a place humans can call home.
Underground lunar living. Lighting and agriculture could be powered by solar panels above the lunar surface. Living underground might seem unusual, but it would allow humans to walk in shirt sleeves inside walls of ancient stone, protected from the airless void just meters away. Every astronaut is a mechanic. Space travelers must always be ready to fix their ship. There are no repair shops or rescue vehicles waiting in space. When equipment fails, the crew must repair it themselves, whether they are doctors, scientists, or pilots. Astronauts train extensively to replace wires, swap valves, patch leaks, and rebuild machines with limited tools and no gravity. They practice underwater in mock spacecraft and through virtual reality. A broken toilet, a loose panel, or a leaking pipe must all be fixed while floating in a suit. Mars missions will make this even more critical. Crews may be months or years from outside help. Space travel turns every explorer into an engineer, a mechanic, and a problem solver. Survival depends on creativity, cooperation, and constant readiness. Protecting spacesuits. A single bolt can scratch a spacesuit. Spacesuits may look tough, but they are surprisingly delicate. Each suit contains multiple layers of fabric, insulation, and pressure seals that create a pocket of life in the vacuum of space. A scratch or tear can cause a dangerous leak. Astronauts inspect their suits constantly, move carefully around equipment, and rehearse every motion before spacewalks. Tools are designed with smooth edges, and spacecraft surfaces are rounded or padded. The vacuum outside has no mercy. A small mistake can turn a scientific mission into a rescue operation. Voyager 1,
humanity's first interstellar messenger. The first spacecraft to leave the solar system is still sending messages. Launched in 1977, NASA's Voyager 1 studied Jupiter and Saturn before crossing into interstellar space, farther from Earth than any human-made object in history. It still sends faint radio signals carrying scientific data on magnetic fields, particles, and cosmic radiation. Voyager 1 also carries the Golden Record, a collection of music, greetings, and sounds from Earth, meant for any intelligent life that might find it. Long after Earth changes, Voyager will drift among the stars, a tiny reminder that a species once lived on a blue planet and reached for the sky. Mars colonies, closed ecosystems. A successful human settlement on Mars cannot rely on constant supplies from Earth. The distance, cost, and risks are too great. Instead, a colony must function as a sealed ecological system. Water will be collected from ice or atmospheric moisture, purified and reused. Plants in pressurized greenhouses will convert carbon dioxide into oxygen while providing food. Waste will be broken down and recycled into new crops. Airlocks will separate the habitat from the barren landscape outside. Energy could come from solar farms or small nuclear reactors stored for the long night. Even clothing, tools, and spare parts will need to be repaired or recycled on site. The colony must function like a living organism, balancing every resource carefully. If it succeeds, it proves humanity can not just visit other worlds, but build new homes on them. Spacecraft doors, lifelines in the void. In space, a door is not just a barrier, it is a lifeline. The air inside a spacecraft is the only air the crew will breathe for months or years. A single flaw in a door seal can let oxygen escape into the vacuum, where it is gone forever. Airlocks and hatches must withstand pressure differences equal to a powerful explosion. Engineers build multiple layers of protection, rubberized gaskets, metal rings, and locking mechanisms that secure in several directions. Astronauts constantly test every seal, feeling for leaks and listening for the faintest hiss of escaping air. On a journey to Mars or beyond, there will be no help coming if something fails. These doors are more than portals. They are the difference between life and death.
The moment we leave Earth behind, everything we rely on vanishes. There's no air to breathe, no ground to stand on, no weather, no sound, no life. Space doesn't care whether we survive, but still, we go. We build rockets hotter than the surface of stars. We train astronauts to do what seems impossible. Against all odds, we keep the human body alive where biology itself begins to fail. Space travel is not safe, natural, or easy. It is bold, it is terrifying, and yet it is the only path forward if we want to see what lies beyond our world. If you enjoy these quiet journeys, consider liking, subscribing, or leaving a thought below. It helps other sleepy souls discover this channel. But for now, all you need to do is relax. Let your mind soften, slow your breathing, and allow yourself to drift gently into rest. Spacesuits, tiny personal spaceships. A spacesuit is far more than clothing. It's a one-person spacecraft designed to keep a fragile human alive in a place with no air, no ground, no weather, no sound, no life. Space doesn't care whether we survive, but still, we go. We build rockets hotter than the surface of stars. We train astronauts to do what seems impossible. Against all odds, we keep the human body alive where biology itself begins to fail. Space even has a smell. Astronauts returning from spacewalks describe metallic, burnt spake, or welding-like scents clinging to suits and tools. These odors result from high-energy particles interacting with the spacecraft's surfaces, a rare sensory bridge connecting humans to the void. Bones weaken almost immediately in microgravity. Without gravity's constant pull, calcium leaves bones and enters the bloodstream,
causing strength loss and strain on the kidneys. Astronauts counter this with hours of daily exercise on specialized machines. But some loss is inevitable, and recovery on Earth can take years. The Sun, shadows, and spacelight. Outside Earth's atmosphere, the Sun appears as a fierce, blinding white sphere against a pitch-black sky. Shadows are pure darkness, with no gentle gradient to guide perception. This extreme contrast affects how astronauts see depth, operate cameras, and even manage solar panels. The Sun reminds us how Earth shields us, softening starlight in ways we rarely notice. Food, sleep, and life's small challenges. Food in space must be safe, stable, and crumb-free. Tortillas replace bread, drinks are stored in sealed pouches, and fruits are irradiated to kill bacteria. Taste changes too. Astronauts often need stronger flavors because fluid shifts and nasal congestion dull the senses. Cooking becomes engineering. Meals must nourish without risking contamination. Sleeping requires being strapped into padded cocoon-like bags to prevent floating into equipment or fellow crew members. Even crying behaves strangely. Tears form floating blobs that cling to the eyes instead of falling. Every small bodily function reminds us how far from home we truly are. Spacewalks are among the most dangerous activities. A tiny tear in a suit could be fatal, and temperatures swing from blistering heat to freezing cold. Astronauts train underwater to prepare, but every excursion into the void carries unknown risks. Adapting to microgravity. In orbit, even simple movements become puzzles. Objects don't fall, muscles don't stabilize automatically, and every motion must be relearned. Microgravity affects not only the body, but also the mind, challenging how astronauts feel at home in their environment. Space radiation presents another invisible danger, damaging DNA and increasing the risk of cancer or weakened immunity. Fires behave unpredictably, forming spheres instead of rising flames, and daily exercise becomes essential to maintain strength. Cold welding, where bare metal surfaces fuse together, is yet another reminder that familiar rules don't apply in space. Even taste shifts dramatically. Food that seems flavorful on Earth can taste bland, prompting cravings for strong, spicy, or tangy dishes. Maintaining nutrition and morale becomes a science in itself. The challenges of long-duration missions. Space sickness strikes many astronauts in the first days of orbit, caused by conflicting signals from the inner ear and eyes. Tiny meteorites create shooting stars visible from within spacecraft, a humbling reminder of the cosmos outside. Growing plants in microgravity requires careful engineering, but it is crucial for long-term missions, offering both nourishment and hope. Blood circulation shifts, faces puck up, legs thin, and hearts can shrink. Spacecraft interiors are never silent. The constant hum of fans, pumps, and electronics forms a rhythmic background that astronauts learn to live with. Viruses may become more active in space, emphasizing the need for vigilance on long missions. Hygiene, tools, and lunar dust. Water behaves like tiny floating planets, requiring careful wiping to stay clean. Lunar dust is jagged and destructive, able to damage suits and equipment. Even haircuts demand vacuum-powered clippers to contain drifting strands. Gloves make simple tasks extraordinarily difficult, and tools lost in space can orbit Earth indefinitely, adding to the growing problem of debris. On Mars, every breath must be manufactured. Oxygen must be generated from carbon dioxide or extracted from frozen water. Habitats require constant maintenance and backups, and the first explorers may stay permanently, building a new home in a harsh, alien world. Rockets, temperature, and Martian skies. Rocket burns in space are delicate, precise, and unforgiving. Without atmosphere, flames behave differently, and fuel must carry its own oxygen. Spacecraft face extremes of heat and cold, requiring insulation, radiators, and careful engineering to survive. Martian sunsets are blue, unlike anything on Earth. Iron-rich dust scatters sunlight in ways that transform the sky into a subtle watercolor of blue and warm tones. Future explorers may witness these sights firsthand, seeing sights no human eyes have ever seen before. The threat of space junk. Earth's orbit is crowded with debris, abandoned satellites, fragments, and even lost tools. Moving faster than bullets, even tiny pieces can puncture a suit or shatter a spacecraft. Space junk is one of the biggest hazards for exploration, emphasizing the need for careful planning and constant vigilance. Conclusion: space is a realm of extremes, where survival demands ingenuity, courage, and adaptation. Every breath, every movement, every meal is a triumph over the void. And yet, amid danger and uncertainty, there is wonder, a universe so vast, silent, and beautiful that it continues to call humanity beyond our home.
The thin wall between life and void. Spacecraft doors, airlocks, and suits are the thin, invisible barrier between life and the void. Every safety system, every seal, every layer of protection keeps humans alive where nothing else can. Building homes with Martian dust. Sending building materials from Earth to Mars would be astronomically expensive. The only practical solution is to use what is already there. The iron-rich Martian soil, known as regolith, can be transformed into durable building blocks through heating, chemical binders, or even 3D printing techniques. Scientists are also experimenting with biological glues made by engineered bacteria. These materials can create pressurized habitats, storage bays, landing pads, or roads. Learning to work with Martian dust does more than save resources. It allows humans to turn an alien landscape into home. Losing sense of up and down. In microgravity, our natural sense of direction disappears. Astronauts float freely, rotating in any direction like swimmers in an endless pool. Without gravity, the brain struggles to decide what is up or down. Some adapt quickly, but others experience lasting confusion. Long-term exposure can shrink brain regions responsible for orientation, creating challenges when returning to Earth. Children born and raised in space may grow up without instinctive up and down, navigating instead by walls, lights, and symbols. Lightning and water beyond Earth. From space, lightning storms reveal their full scope. Jagged flashes erupt across thousands of miles of clouds, some even reaching upward into the sky, invisible from the ground. Rare phenomena like sprites and elves become visible, illuminating the power of Earth's atmosphere. Earth is also the only place in the universe with flowing fresh water. Mars's water is frozen or salty, icy moons hide oceans beneath kilometers of ice, and comets contain only vapor or ancient ice. Every glass of water on Earth is a cosmic treasure, a reminder of how unique and precious our planet is. The first human footprint on Mars. The first human footprint on Mars will symbolize more than exploration. It will mark humanity's evolution into a multiplanetary species. Children born afterward will grow up under two skies, expanding art, culture, and identity beyond Earth. That first step will be quiet, yet its echo will resonate through history. Computers in space. Space computers must withstand cosmic radiation. High-energy particles can flip memory bits, crash systems, or destroy circuits. Spacecraft use hardened processors, thick shielding, redundancy, and error-correcting systems. These computers work slower than terrestrial laptops, but are far more reliable. From Mars rovers to deep space probes, durability is life itself. Hibernation for deep space travel. Journeys to distant planets or stars may take decades or centuries. One proposed solution is hibernation, slowing metabolism, heart rate, and body processes while machines handle the voyage. Crews would need less food, water, and oxygen, while avoiding the psychological strain of long-term confinement. Aurora from above. From orbit, auroras appear as glowing rings around Earth's poles, pulsing and dancing above the thin atmosphere. Charged particles from the sun collide with gases, creating waves of green and red light. Seen from above, they are reminders of Earth's energy, life, and fragility. Generation ships. Travel to other star systems may require entire generations to live and die on board ships designed as self-contained worlds. Schools, food systems, and medical facilities would exist within, creating new cultures, societies, and laws. The descendants may one day step onto a new planet, carrying forward the legacy of the original crew. These journeys are not just across space, they are across time itself. Return to home. As we drift back from this voyage into the stars, return to the quiet comfort of home. Let the wonder settle in your thoughts. Beyond the blue air we breathe lies a vastness full of mystery, beauty, and possibility. Our imaginations are free to wander, weightless like the universe itself. If this journey brought you peace, remember to like, subscribe, or leave a thought in the comments, helping others discover this quiet corner of curiosity. For now, close your eyes, feel the soft pull of rest, and let the universe fade into stillness. You are safe, you are warm, you are drifting through the stars. Good night. The thin wall between life and void. Spacecraft doors, airlocks, and suits are the thin, invisible barrier between life and the void. Every safety system, every seal, every layer of protection keeps humans alive where nothing else can. Building homes with Martian dust. Sending building materials from Earth to Mars would be astronomically expensive. The only practical solution is to use what is already there. The iron-rich Martian soil, known as regolith, can be transformed into durable building blocks through heating, chemical binders, or even 3D printing techniques. Scientists are also experimenting with biological glues made by engineered bacteria. These materials can create pressurized habitats, storage bays, landing pads, or roads. Learning to work with Martian dust does more than save resources. It allows humans to turn an alien landscape into home. Losing sense of up and down. In microgravity, our natural sense of direction disappears. Astronauts float freely, rotating in any direction like swimmers in an endless pool. Without gravity, the brain struggles to decide what is up or down. Some adapt quickly, but others experience lasting confusion. Long-term exposure can shrink brain regions responsible for orientation, creating challenges when returning to Earth. Children born and raised in space may grow up without instinctive up and down, navigating instead by walls, lights, and symbols. Lightning and water beyond Earth. From space, lightning storms reveal their full scope. Jagged flashes erupt across thousands of miles of clouds, some even reaching upward into the sky, invisible from the ground. Rare phenomena like sprites and elves become visible, illuminating the power of Earth's atmosphere. Earth is also the only place in the universe with flowing fresh water. Mars's water is frozen or salty, icy moons hide oceans beneath kilometers of ice, and comets contain only vapor or ancient ice. Every glass of water on Earth is a cosmic treasure, a reminder of how unique and precious our planet is. The first human footprint on Mars. The first human footprint on Mars will symbolize more than exploration. It will mark humanity's evolution into a multiplanetary species. Children born afterward will grow up under two skies, expanding art, culture, and identity beyond Earth. That first step will be quiet, yet its echo will resonate through history. Computers in space. Space computers must withstand cosmic radiation. High-energy particles can flip memory bits, crash systems, or destroy circuits. Spacecraft use hardened processors, thick shielding, redundancy, and error-correcting systems. These computers work slower than terrestrial laptops, but are far more reliable. From Mars rovers to deep space probes, durability is life itself. Hibernation for deep space travel. Journeys to distant planets or stars may take decades or centuries. One proposed solution is hibernation, slowing metabolism, heart rate, and body processes while machines handle the voyage. Crews would need less food, water, and oxygen while avoiding the psychological strain of long-term confinement. Aurora from above. From orbit, auroras appear as glowing rings around Earth's poles, pulsing and dancing above the thin atmosphere. Charged particles from the sun collide with gases, creating waves of green and red light. Seen from above, they are reminders of Earth's energy, life, and fragility. Generation ships. Travel to other star systems may require entire generations to live and die on board ships designed as self-contained worlds. Schools, food systems, and medical facilities would exist within, creating new cultures, societies, and laws. The descendants may one day step onto a new planet, carrying forward the legacy of the original crew. These journeys are not just across space, they are across time itself. Return to home. As we drift back from this voyage into the stars, return to the quiet comfort of home. Let the wonder settle in your thoughts. Beyond the blue air we breathe lies a vastness full of mystery, beauty, and possibility. Our imaginations are free to wander, weightless like the universe itself. If this journey brought you peace, remember to like, subscribe, or leave a thought in the comments, helping others discover this quiet corner of curiosity. For now, close your eyes, feel the soft pull of rest, and let the universe fade into stillness. You are safe, you are warm, you are drifting through the stars. Good night.